Hello dear students, welcome you all. In this lecture, I am going to discuss about the basic ideas of statistical physics, right? Basic ideas of, right. So, in this lecture, we will discuss about what is the need of statistical physics, what is statistical physics, what are the different branches of the statistical physics, and how they explain different phenomena in physics, right? So statistical physics, right, it is made up of two words, statistical and physics, right? Statistical is basically originated from statistics, right? Now, what is statistics? We know statistics is basically a science of the collection, classification, and interpretation of numerical data, right? So, when we have very large data, large numbers, and we want to get some results from that data, then what we do? We collect that data, classify that data, arrange that data in a particular order, and then we apply suitable mathematical tools on that data. So then that data tell us about some features of that system, right? So this is statistics, right? Now, when these statistical methods are applied in physics, then that branch of physics is called statistical physics, right? Statistical physics, right? So statistical physics is basically a branch of physics that deals with the study of the physical behavior of a physical system that contain large number of either atoms, molecules, right, or nuclei, or even electron, photon, whatever it may be, right? So here we are dealing with the a physical system, right? Instead of dealing with the simply mathematical numbers, here we are dealing with the properties of physical systems in statistical physics particularly, right? So what is the need of statistical physics, right? The question arises, why we require statistical methods to be applied in physics, right? What is the need? So if we look at the various properties of systems, like if I consider a gas contained inside a container, right? Let we have a gas that is contained in a container. This is a container, right? And we have a collection of a particular gas inside this container, right? This container is containing a gas, right? Now we know this container will have a very large number of gas molecules, right? If it is sorry, we know 1 centimeter cube, 1 cc of a gas contain around 10 raised to power 20 gas molecules, right? So we can say that this is the given area in which a given container enclosure in which we have some gas, then the number of gas molecules will be very very large, right? Now if I want to find out some properties of this gas, right, like its pressure, its volume, its temperature, right, then what I can do, because this entire system is made up of very large number of particles, very large number of gas molecules, and these gas molecules or particles are so small that I can't measure the temperature of a individual atom, individual gas molecule, individual particle, right? So in this case, we have to take the help of statistics, right? We have to look at the average behavior of this entire system, right? So instead of looking at a particular atom, molecule, or a particle, we will look at the entire assembly as a whole, right? And we will apply these statistical tools for this entire assembly. We also know one fact from the statistics, that the results of the statistics become more and more accurate when the number of entries or number of particles or number of participants involved are very large. So obviously in physics we have large number of participants, right? It means the whatever results, whether it is linked with pressure, volume, temperature, energy, or some other property of this gas contained in the container, we will get more and more accurate results when we will apply statistical tools to find out these properties, right? Because here we are limited, we can't go to the property of a individual gas molecule or gas atom. So we apply these methods here, right? Now, in physics, this was the general case when we took the case of a gas contained inside a container. But in physics, we can have different systems, right? We can have even a collection of electrons, clear, or collection of photons, right? In that case, now when we have a collection of electron or photon or neutron or proton, then this system becomes totally different from a classical system, right? It means now we have to take a different approach. We will apply statistical tools, but we can't apply these statistical tools directly. We have to develop another branch of statistical physics, right? So according to this entire discussion, we came to know that in statistical physics we will have two branches, clear? One is a classical and other is a quantum, right? So classical means classical physics problems, clear? Means the system with which we are dealing, clear? It contain gas molecules, atoms, right? Classical systems, right? What when I talk about the quantum systems, right? Quantum means they are electrons, photons, neutrons, protons, right? Elementary particles basically, right? So this is the difference between these two branches of the statistics, clear, that we must have in order to apply statistical methods to the problems of physics, right? So classical statistics basically deals with classical systems. It include gas molecules, atoms, right? Or even it can be another kind of a system where we have some kind of balls, right, or other particles, right? But in quantum statistics we will exclusively deal with the quantum particles, right? Particle which are present inside the atom like proton, neutron, electron, photon, etc., right? So this is classical, this is quantum. Now classical statistics is basically developed by Maxwell and Boltzmann, right? So it is also called as a Maxwell-Boltzmann statistics, clear? Whereas quantum statistics again can be divided into two parts, right? How? Because we know in case of quantum physics we have two type of particles. One are bosons and other are fermions. Both these particles have different properties, right? I mean, this obey Pauli's exclusion principle, but bosons don't obey, right? So both these quantum particle needs two different wings of statistics, right? So we have two wings, Bose-Einstein, that was developed by S.N. Bose and Albert Einstein, and then we have Fermi-Dirac, Enrico Fermi and Pauli Dirac, right? So these are two branches of quantum statistics, right? And this is a classical statistics. Although classical statistics is enough to explain various phenomena in physics, like it helps us to know about the pressure, volume, energy, temperature of a gas, right? It also gives us about the idea of the speeds of gas molecules, right? Right. It gives us the distribution of the speeds inside the gas. It gives us the distribution of the energy inside the gas, right? But when we want to know the properties of quantum systems, right? Like we want to know the spectrum of a black body radiation, or we want to know the energy of a electron gas. In that case, this statistics is not enough. So we need quantum approach, right? So this is the overview of this entire course that we study in this class. The course was statistical and thermal physics. So the first part is statistical physics, right? So it is clear that when statistical methods are applied in physics, we have two wings of physics, that is classical statistics and quantum statistics. Classical statistics is mainly consist of Maxwell and Boltzmann observations, their results, whereas quantum statistics contain the results of both Bose-Einstein as well as Fermi-Dirac, right? If I do a distinction between these two branches of statistics in terms of the particle involved, as I told you, it deals with classical particles like gas molecules, right? Most common. It deals with the quantum particles. There are some rules which are followed in both these branches of statistics. Like in classical statistics, the particle are identical and distinguishable, right? There is no restriction on a particle entering in a cell, clear? Whereas in quantum statistics, clear, the particle are identical and indistinguishable. This is very, very important, clear? And in case of bosine, there may be restriction. I can say there may be restriction. We have seen that in case of Fermi-Dirac, there is restriction. Only one particle can enter in one cell because of a Pauli's exclusion principle. But in Bose-Einstein, there is no restriction. It means I can say there may be restriction. But in classical statistics, there is no restriction. Clear? The particles are identical and distinguishable. Why they are distinguishable? Because in classical physics, we can measure both position as well as momentum of the particle simultaneously. So I can say which particle is which. But in quantum statistics, right, the particle involved are a quantum particle, and there is uncertainty principle which restrict us from measuring both position as well as momentum simultaneously. Also there is overlap of the wave functions of the individual particles. We know in quantum physics we represent the particle by the wave packets. So when we have more than one particle, their wave function overlap. So it is very difficult, impossible to tell which particle is which, right? So it means the particle are both identical as well as indistinguishable. Whereas in classical, even we can distinguish identical particles, right? And this was the second condition. So these two conditions are the broader distinction between these two branches of statistical physics, right? So thank you very much.